Hello, good morning. So today we're going to be looking at shifting and stretching functions in this submodule. I'm going to keep my piece pretty brief because I've actually got a lot of supplementary videos and practice problems to just play with these ideas, which I think is the most important. But I did want to give like a high-level overview of what we're doing here. So this unit is about shifting and stretching the library of functions that we're already building. Sometimes they're called the parent functions. And so this applies to logs, the logarithmic function, the natural logarithmic function, and any base because they are functions. But it also applies to all the functions we've encountered before, as well as the ones that are up and coming. To preview, we're going to be looking at trig or periodic functions moving forward. So these principles will apply to all of them. So I want you to kind of keep a big picture mindset with this, that this doesn't just apply to logs, it applies to all the functions that we work with. So the main idea that we're looking at here is one of starting with some general rule, y equals f of x, and since it's on top of our minds, let's say that we're thinking of the rule log x. And if we introduce some parameters to this, I like to call this the vanilla function, right? Because it's just the base function with nothing added to it. It's just the log of whatever you input. But then we can add some flavors or parameters that are going to shift and stretch the original vanilla function into something else. So A, B, C, and D, you're going to see these sometimes present, sometimes not present, and they would be as real numbers. So, you know, the real numbers you know and love. And they alter the function. And so our job in this unit is to understand what each of these does for all functions. And so I'll give you a little bit of preview right now. And again, what would this look like for the log function? This would look like a times log of bx minus c plus d. So what does this mean compared to this? Well, if we look at an example where I actually have some real numbers and they're not just in the general form, let's say I look at, log x versus 5 log 3x minus 4 plus 2. How does the graph of this function differ from the graph of this function? What I want us to pick up in this unit is that it's going to have the same general shape or relationship, but it's going to be shifted and stretched. So the question is, how is it shifted and stretched? Well, let's remember how the regular log function looks. When we graph it, it passes through 1, 0. Has a vertical asymptote at x equals 0. And now how about this different version? So if this is y1, how about y2? So each of these parts contributes something to the graph. This here scales the y value up by a factor of 5, right? So imagine what the y value should have been, say, here. And now that's getting multiplied by 5. So we could imagine it's going to be maybe way up here. And it's also being added a value of 2, a flat value of 2. So it's actually going to be a little bit higher up here. So if we think about that, we might have a graph that's been shifted up if it just had these parameters, this A and this D. But we know B and C are also doing things to this graph. So what's happening there? So in general, the inputs are messing with the horizontal stretching and shifting. So this 3 is also a scale factor of the inside, right? So it's scaling the input directly. So you can think of this as kind of accelerating the curve. It's shrinking it down because you're eating up those inputs faster, right? An input of 1 is now 3. An input of 2 is now the input of 6, right? So it's taking the log of 6 and putting it where the log of 2 was going to go. So it's kind of smushing it down in this direction. So you can think of it as shrinking it or smushing it down when this number is larger than 1. And when it's less than 1, it's going to be stretching it out because you're going slower. Okay, so that's tough to draw, but I'll show you in Desmos how that looks in a moment. And then the last is this is the slide, the horizontal slide. And what this does is it also fast forwards you in time. The way to think about this is if I had an input of 6 for x, an input of 6 for x on the regular log curve, right, that is now where the position would be at x equals 2. So it's moving it over in this direction. Okay, so I'm going to show you on Desmos how that looks because this graphic's getting a little crowded. So let me show you how we would do this. If you enter a function with these parameters a, b, c, and d into Desmos and you're using y and x for your variables, it will kind of know that you must mean these to be parameters and you can add them all as sliders. So I'm going to set these to a being 1, b being 1, c and d being 0 so we can see what happens. So right now it's equivalent to the log x function, right? Because a is 1 and b is 1. Now when I start to mess with these things, we'll see the effect they have on the graph. So we said a scales the output up and down, right? It multiplies it by the scale factor. So if I increase a from 1, it's like taking that output and increasing it by a scale. So here is taking all those and increasing it by 5. For b, I said this is like we're scrunching the function down. So you can kind of see how this is happening. So just zoom out a little bit here. So here you can see it's kind of scrunching the function down in a horizontal way. I know it kind of looks like it's going up, but it's really taking all of the change and smushing it into a smaller window. So we said that was at 3 for our example. The plus 2, again, this was the lift, right? This just simply takes the function up and down. So we had a lift of 2 in the positive direction, so it went up. And then c is the slide. And so you'll notice it's being subtracted, which really means it's putting it forward in time. So if I increase c, it's going to move it to the right, right? Because now an input of x equals 1 on our original log curve, that's where this function has a 0, crosses the x-axis. That's not the case on the green function. Where did the 0 go for the green function? Well, it's been shifted to the right. It's also been shifted up and over. Since we have a lot going on here, it's kind of lost in the mix. But we do see that the effect that this has been shifted over, right? So if you input 1 for x, you'd get 3 minus 4, which is negative 1, which means it's actually undefined, right? Because we have a log. You can't have a log of a negative number. We can only take a log of non-negative numbers. So you would see that log of 1 is actually behind the vertical asymptote, so we wouldn't have a definition here. So it's been moved to the right. So if I just want to isolate this particular parameter, just c, and we can compare what happens. Let's set c to 0 and start over. So red is my original and green is my new function that's been slid over. Here it's been slid over 2 or shifted over 2 to the right. And why is that the case? Because an input of 3 for x is really the original curve at an input of 3 minus 2 is 1. So this looks like the exact same curve, it's just been shifted over 2. So that's why I say it's kind of been moved forward in time. Subtracting some value off of the input is like fast forwarding through time, if this is the time axis. So if we negate it and go the opposite way, right, which really, if we're subtracting a negative number looks like addition, then you're really rewinding in time, right? You're giving something back to the input, so it's sliding it backwards. So when C is positive, again subtracting a negative, you'll see it shift left, and when it is positive and you're subtracting, it's really moving it forward in the curve. So that is one place where people often get confused, because you'd think to the right means positive, but really you have to think about that we're taking it off the input, so it's really kind of sending it forward down the axis. So you will have a chance to play with each of these things. I just wanted to give you a very, very quick overview of what each of these dials really does to the function. And again, the understanding here is really going to come from the interactive examples. So I will leave you to those. Enjoy! So why are we doing this? Well, this general shape, y equals log x, does have some applications, but really when we fit these relationships that have this general shape to the real world, they have particulars, and these particulars are going to come in the form of these parameters, right? Just like the line y equals x doesn't really model that much in the world, but y equals 20x plus 10, this has some parameters in it that shift the original line, and this might be a paycheck function, right? Or this might be an average speed function. It comes from the particulars, and it comes from how the average rate of change is affected by those particulars. That's how we keep the function more accurate. So the reason that we do this is to make it line up with the real world. So again, I did this really fast with A, B, C, and D. The goal for this unit is to have you dive into these video tutorials as well as the practice problems. There aren't many in the textbook for this, so we're going to focus more on the online problems. And there should be links underneath a lot of them to help you with a problem should you get stuck. And as always, bring your questions to the class discussion and we will drive it from there. Okay, so enjoy taking these vanilla functions and adding all sorts of flavors and seeing what happens.